So let's get it started. So today we're going to talk about Project 2, the Pintos Project 2. It's user programs. Hopefully you're doing well with Project 1, and there's still like 2 days left. So keep going. So far in the semester we have covered the topics which are we basically also covered in midterm exam, and then after the recess we're going to actually go over the next topics. We're going to start with memory, and we have like file systems, I/O, and some how disk drives and storage basically works. Security, a little bit of the distributed systems, and so on. So the type of the topics is a little bit different, but we're going to talk more about it after the recess, right? In the next 26th session. So today, and then so hopefully you're done by the PA1 implementation. Again, at this point, I hope everyone is like just debugging at priority and alarm clock, MLFQS. If you're struggling with it, it's the last part. It is like also separate, so it's it's fine. But at least hopefully you're getting the other parts done, and make sure that you are submitted. I saw that a lot of the groups were not submitted on AutoGrader, so actually I ended up moving all the groups from previous assignments, your design doc, to the code. Just verify if you have any mismatch or anything. Just verify. Right now your groups are basically just like transferred, and make sure you actually submit. There are a lot of groups who have not submitted their source code. Source code is different than design doc. Even if you didn't do submission on design doc, that was just like one submission. Your file would be there as long as you submit it. AutoGrader, you might get some reason you get a 0, right? We don't have time tomorrow, you don't have time, so submit and make sure whatever you're submitting, you're getting the same grade in AutoGrader. Otherwise, let us know, and then there is time for us to fix it, or at least take a look at it. Otherwise, it will be difficult. The grading will be postponed because you have to download every submission manually, submit and grade. And again, if the grade doesn't match, then we have to ask for you to bring your laptop, whatever. It's just like gonna make a lot of trouble. All right. So today we're going to talk about Project 2 user programs, and again, 5 steps: preparation, understanding with the Pintos code about it, and how user programs are defined and run in Pintos. And then again, you have the design doc and also the implementation. So this project is going to be definitely need more work from your side, both in terms of logistics and work. And I'm like emphasizing on both because we want to, instead of like, because you've gone already through Project 1 and logistics, so, you should like feel more responsible to follow instructions, creating your group, submitting and all this, because then, the teaching staff's time can be more focused on your problems and issues with the, actual, coding, implementation, questions, whatever, alright? So if you remember, this is the Pintos full implementation code after Project 4, which you're not going to implement. And so you started with this before Project 1, and it was just like basic kernel, and then you started implementing some of these MLFQS, alarm clock, priority, and priority scheduler. And then in the second project, you're going to actually go over here and implement the system call layer, which is the way user programs and operating systems interact, and the user programs actually request operating system to do I/O for it. And also process management, which is again part of the kernel that need you need data struct and communication, synchronization in order to have a harmony between the like processes, how a process gets created, what new information you need to keep. And we're going to talk about them a little bit more today, all right? So, first thing first is that, again, if you have not, take a look at the Pintos documentation. So, I'm going to ask here and ask you to raise your hand if you have like covered, Pintos documentation for Project 1. Did you go over Chapter 1, Chapter I think it's wrong. It is a typo. So chapter 2 or 3, which was for Project 1, the reference guide and debugging tools. Did you go over it? Raise your arms. Okay, that's actually good. Okay, so I hope you actually use those information, both as a student. I mean, I didn't go over the documentation a lot after the student, because once I submitted the project, I was just like, done, right? But then when I was TA, I was looking at the documentation, I was like, oh, when I was a student, I did not like actually pay attention to all these information, which were like pretty useful, and I was like struggling, and these could actually help me a lot, right? So that, like, the Pintos documentation itself, like, gives you like valuable information. And you have to go back to it every now and often, because first time you read it, actually you don't understand what's going on. And then you dive in and struggle with the code, and you understand some pieces of code. Next time you go to the documentation, now, like, things make sense. Like, you have like visions, right? So, again, for Project 2, make sure you actually cover the Project 2 section completely. Also, there are a bunch of other reference guides for this project that you need. The debugging will be more important in Project 2, because unlike Project 1, you can't just throw printfs everywhere that you want. It's not that easy. Try also not to miss recitations. The TAs will actually try to provide you with useful and valuable information for your project. Try to make use of them. Otherwise, you'll have like more trouble down the road, right? So we're trying to, like, prepare and then give you information that help you implement. All right. So project number 2 does not depend on project number 1. This is the first thing that you need to know, even if you're like, it does not matter at all, because you're just like going to start with the same fresh code that you started for project 1, right? Because the user programs, they don't have priority, they don't need multiple level feedback queue or anything, they don't have inheritance or anything, they are going to be like one at a time. So, we're just going to go back to the basic round-robin scheduler that Pintos had, everything that it had, right? So, once we set up the GitHub Classroom, the repos will be reset to the initial one. So you have to, again, kind of start the same process. We're going to give you the instructions, so just make sure this time pay more attention to the instructions and follow the steps one at a time, so we don't have issues with group names or repos or anything like that. This time we might give you a prefix for your project 2 groups. It's just pay attention to such things. And don't worry if you've messed up, if your kernel crashes or anything. It does not matter for project 2. And yeah, so this time it is, again, a little bit more on your shoulder to watch out for, to follow instructions, to, not fall behind, not have any mismatch or anything, okay? So we're going to first understand what is going on in Pintos, and this is the important part, because you might have an idea about user processes and memory, but how it is laid out in Pintos and how things work there is important, right? Because that's where you're going to start modifying and implementing. Okay, so a simple C program that you've used, is just you have main, and then you use a bunch of stuff, maybe you printf, and then that's it, right? So this is a simple program, but there is much more behind it, and what's going on. So the first thing first is that whenever you compile this, there are a lot of things added to it, right, that you don't see. The things, for example, that are in library. How the printf actually was working, you don't know down, under the hood. There are a lot of system calls and I/O behind this one. Or even the simple main here, that doesn't mean, because you're not having any arguments in main or any return type here, that doesn't mean that they don't exist. The compiler fills in for you. What is a main? It's like a function. So where are you returning from this function? You're not, right? There are, again, the compiler understands the domain and, sets up this entry point, and then, make sure that at the end of it, it exits as a process, and, so there are a lot of, extra things that are added to this. And, now, one thing that you might have used is, arguments. Whenever you want to actually call a program and give it arguments, right? So, for example, you compile this, and then you run this with your test programs, and then multiple arguments. How are that gonna be handed to the program? Because the program is an executable file, right? So how does it know what is passed to it, right? So the way that it is to do that is through these arguments, right? So even if you don't put these there, the stack will still look like whenever you're like calling into the main, it's as if you're calling a function, right? So definitely whenever you're calling a function, there will be something in the stack, right? And so in this stack so the program needs its arguments in its stack, right? If you don't have any idea what I'm saying, like, the stack, and just raise your hand. I know some of the students like don't have the background for that, but I want to at least adjust what I'm saying. Everyone knows about like, when a function gets called, things are in the stack. Okay. So when we're calling this function and we're putting in arguments in its stack, it doesn't know how many they are, it doesn't know how long they are, right? There's no way to communicate this except that first, or basically last in the stack, which is first accessible to the program, is the number of arguments, and then the arguments above that, right? And so when a program just like starts, it does not have any idea, have I been given any arguments? Have I been like given like 1, 2, 3, whatever, right? It doesn't know. So it just like looks at its stack and then reads, okay, I have been called with 3 arguments. And then looks above that because it knows whoever called me, the operating system, has prepared me enough information, right? I depend on the OS, so I'm just going to take a look at my arguments. And then the argument's going to be above that, and then read those arguments, and then, for example, print them. So, but you are that operating system. Right now, there's nothing up there, right? So your role in the user program in the argument passing is to set up that stack. All right? So, also the system calls. This printfs, or, opening a file, writing anything into the file, closing the file. All of these are system calls. Whether you want it or not, whether you knew about it or not, they're system calls, because you cannot just let the, programs access any files. Maybe those files are not theirs. Maybe they don't have access. Maybe they're not, they're just only readable, whatever. The user programs, you cannot rely on it. And you have to let the OS handle this, and the user programs actually go through specific system calls to ask in a specific format that, hey, I want this file. I want it to, read it. I want write so many bytes to it. Here are my bytes. Here is this is string, whatever. And the OS should do that. Right now, it's not there, right? This call, it's just not there, right? So you have to implement all those. This fopen is a, call from a library. So it's gonna go down to the library and get compiled. But at the end, it's gonna it's going to call an interrupt, the software interrupt, which is the system call. But that interrupt handler in the operating system side does nothing right now, right? Absolutely. So, whenever you're writing something like this in the shell, you are in the shell. So you are actually in the software already, and a user program. Now, you call cp-r, whatever, you want to copy some files there. So what this does is that the shell, first of all, parses the user input, right? The shell program itself just parses this string, takes a look at your environment variables, look for where the CP is, for example, and all that. Then calls the fork. You've learned about fork. And then calls the execv with the arguments and CP. So the shell will be there. It will ask operating system to create a separate process. Within that process, it will start the program CP, which is an executable, and the rest of the arguments and environment variables, and then starts there. So then that process will be now replaced by CP program. Now the CP parses the arguments, and in the meantime, by the way, shell is waiting for CP. Whenever this happens, shell will be waiting for CP the whole time. Now CP, as a program, parses its arguments and then see what you want to do. It understands what is -r, its recursion. So it now it would expect the directory, and then go ahead and ask operating system, do I have access to this folder? Do I have access to this folder? Do I have to? What are the lists in this directory? And these are all I/O and system calls. And then going through all those files one at a time. Do I have access to this file? Now can I create a file in this directory with that name, and then copy the information, and then again next file. All of this happens, and then after that, It will print out some messages whenever it's like successful, permission denied, whatever. And then after it's done, CP exits. And now shell was waiting for CP. Once shell understands that CP has exited, it will give you back the cursor, right? So now in the Pintos case, let's see. If you take a look at the entry point to your program in threads init.c, you have like main, right? Obviously before that, some of the things in the loader and everything has happened, but from the C program side, you can take a look at the main. And then you follow it, and then it actually calls the run actions with the argue values. These arguments are the command line arguments that you have passed onto Pintos. So when you call like Pintos run whatever, that Pintos actually is a script. It's a Perl script you can find in user bin, I think. And so that by itself does some parsing, but eventually it will call the loader and read some of the arguments that you pass, such as run alarm test, whatever, and then pass those to the run actions. Now the run actions functions call run task, and then the run task is like has one task. So for example, alarm test, whatever, right? In project number 1, because threads are defined and not the user programs, the task is actually just a test. It knows that you are in the kernel. It knows that you're testing the kernel functionality. So it's just like goes to the function which is like there. In the user program, however, because it expects you to call Pintos with a program. So after booting, run this program. Okay? So then in the run task, it will actually call process wait on that user program. And then asks process execute to run that program. Alright? So this is important because this is the entry point to basically, starting that user process. Now, when you go look for that process execute in the process.c, it actually, you can see actually, the kernel creates a new thread. Because threads and like in the Pintos, each process has only one thread. We don't have multiple, multi-threading. You can basically use the same PID and TID as the same thing. So then the process creates a new thread. The initial thread in the kernel is going to be there, but it's going to create a separate thread. And then that thread function is going to be starting the process of that file name. So if that file name is CP, then that CP is a binary file. The thread function should point to the start of that binary file and start executing those. Instead of executing a function in your kernel, it has to go in and start running that binary. Now, start process is a huge deal, and this is where you actually have to pay attention and start modifying, because the start process, you're giving it the arguments, but the whole thing is not a file name. So, for example, here, cp-r user bin temp dot is not the program. CP is the program. The rest is the arguments, right? But you cannot separate these and then send to the send process. You will send the whole thing, and now in the start process, you have to start modifying and parsing. And in the start process, it does a bunch of things, reading and make sure that binary is, that ELF file is valid. Whenever you run a binary, it doesn't just execute. It can tell you, hey, this is not for x86. It is for ARM architecture, or it's not for 64-bit. It's 32-bit, whatever, right? So these are the things in the binary file that the start process uses load that file and then checks these. In the load of that file, there is a setup stack, which is again your job in the argument passing. Whenever you're loading a binary, now you also, based on these arguments that are being passed down, you have to set up a stack for that user program. All right? So I load you here in the memory. I find the entry point to execute, but I set up, I allocate some memory to it as a process, as a thread. Okay, here is going to be your stack. Here is going to be whatever. I'm going to allocate pages. But now whenever I want to actually run, now that user program expects something in the stack. You have to prepare that stack. All right? So you got an idea how user programs start in the Pintos or not? So far you have not done this. Again, your Pintos code never reaches this point so far in PA1 because you run make in threads directory, right? So this is now the memory layout. So we're going to talk about memory more after the spring break. But overall, you understand what, like, how memory, works. And now also you will understand what is a virtual memory, because you remember each user program believes that they have the memory starting from 0 all the way to I think at least 64 megabytes or something. And so what the operating system does with the some extra registers in CPU is that it like full user program whenever it switches to the user mode. So it will tell the CPU that, okay, you have a base register, whatever that user program wants to access, they believe they have like one address, but then you have to translate that address to this part of memory, because I'm the OS, I'm allocating only this part of memory to the user. The user might think, okay, I'm going to access address 100. But that 100 is not an actual physical 100 on, your physical memory. It's going to translate you, right? So from the user perspective, this is the virtual memory. So you have from 0 all the way to the 4 gigabytes addressable memory because of the 32-bit, pointers. Now, there's a physical base, which is the 3 gigabytes, and then your kernel virtual memory starts there. This is not the layout of your physical memory, remember. Your physical memory you will deal with in your Project-3. Don't worry about it. Now, a user virtual memory thinks that it has from 0 to here, and it has some of these numbers. They're not significant. They don't actually mean anything. They're just compatibility reasons that they have their code segment starts at around this address, and then there are segments for data, static variables and initialized data, and then there is block storage segment, and then the heap memory starts, and then at some point there is a user stack, and then this grow as you put stuff in the stack. This is grow as you So they think that all of this is available, but then the operating system dynamically will allocate memory to the user as needed. All right. But the important thing here is that no matter where the stack pointer is, it is somewhere in the memory, and the user program is only allowed to access its stack right below the stack pointer as it pushes things in it, right? Not above it, because that's going to be your actual kernel information, right? So some of these actually will be in your page directory files. You are, welcome to read. Actually, Pinto's documentation also points you to where to look at if you want to, use some of these information. Some of them you don't actually need. So whenever a user program now tries to access an address which is not mapped, right? So user thinks that it has so much memory, but it actually doesn't, right? And the CPU has been given enough information by the OS that, okay, right now, this memory is, you have to translate, and then there is page tables, so the CPU knows which addresses are accessible, and if the user space tries to access some part of memory that it should not have access, there will be a page fault. There's an interrupt that the CPU just jumps, and then OS has a handler, takes a look at it, okay, what's going on? Why did you try to access this, right? Is it a faulty program? Is it just trying to access some data that is not supposed to? I'm going to exit it and I'm going to crash it, right? I'm going to exit that thread and then free up its memory. That's the job of the kernel right now. So that can happen whenever it wants to try to access, for example, above phase base or somewhere that is not mapped. But we're going to change that. Okay, I'm going to tell you in a few slides. So now the first thing first is that you take a dive into this program and definitely not read all of it. Only the files that are mentioned in this document and Pinto's documentation. You don't have to read all about the page tables or that's just extra. And so as I said, Pinto's already supports the loading and running of the user programs. However, it does not do any argument passing. So it just starts executing the program, and that actually will, end up with a fault. I'm going to tell you why. And then it does not allow any, system call. Whenever a user program calls a system call, it ends up in a system call handler, and it does nothing. Okay? So this is the source files that you might want to take a look at. All right? So let's see. The other thing is file system. Okay, so this is important because, again, you have not dealt with this at all in your Project 1. But an actual computer, whenever they want to actually run, right, the kernel boots from like a hard drive, right? And then there are other programs on that hard drive. Whenever you want to run that CP is a binary file in your hard drive that your kernel loads and then access it. In Pintos, your kernel right now does not actually boot from any hard drive per se. Like the loader boots the kernel from somewhere, we don't care, right? It loads it from the object file. But then, when the kernel starts executing, it does not have access to any file system or any device. There's no hard drive. So, but when we want to actually run executables, the kernel wants to access somewhere. Where is that user program? Right? So, Pintos actually provides a file system. Just like your virtual machine that you have, a virtual disk that is a file on your host machine, but it is actually mapped with file system and partitions. So the virtual machine actually reads that file, maps it, and then reads stuff from that. Right? The exact same thing is happening inside your virtual machine and with Pintos. So now whatever I'm talking about as a host and everything, I'm just talking about your Ubuntu in your virtual machine, right? We're just like one level in the inception, right? So your host or Ubuntu will have a file, a desk file, tiny, like 2 megabytes. That's more than enough for us, right? When Pintos loads, you have to let it know that, okay, you're going to use that file as your file disk. And then you're going to format that file and then have it partitioned. After you have it partitioned, you can use the Pintos script to put files, executables, into that 2 megabyte file. Then when Pintos boots up, because it is now in your Project-2 and user programs, it actually understands that, okay, I have a device, I have a storage, and it is, accessible, it has a file system, and then it tries to load information from that. So if you have like the CP program inside that, then the Pintos can actually load that file from that file. Alright? So you don't have to change anything in the file system, but you have to know how it works because you need to use the scripts to create that file disk, to format it, to put executables in it, right? So it already exists and has implemented. You do not have to modify the file system at all. But you can use the file H and file C to take a look at how Pintos accesses files within that device, right? And there are similar, not with the same name, similar functions to open a file within that partition with a name, to close a file, to read from a file, or write to a file. Everything again happening in that virtual disk. All right? Any question? All right. So it has limitations because it is meant only for your testing for projects. So first of all, it does not have any synchronization. So two different parts of two different threads within the kernel can call those functions and access that file, and things can just go wrong. The file size is fixed at creation time. Whenever you create a file within that virtual disk, the file size is just like fixed right there. You cannot like change it later. It is like in a contiguous range of sectors on that disk whenever you create a file. So your Linux, it doesn't do that. Like if you have a gigantic file, it is not a contiguous sector of your hard disk. It will be chunked and then linked. We're going to learn about it in second half of the semester. There is no subdirectory. There's no directory. That file disk is just like a bunch of files, right? No, nothing. Just simple. And they're limited to 14 characters with file name. So you cannot have a file name of 15 characters. But again, it will be enough because whatever that we want are executables such as echo, args, simple files. And a system crash from the kernel can easily corrupt that hard disk. It's like a partition and file system, right? It can get corrupted, and then Pintos cannot access it and read it. So easiest thing is from your host, which is your Ubuntu, whenever you format it, whenever you put your files, you just make a hard copy of that file, and whenever you want to restart your Pintos or anything, you can just replace that old file with the fresh safe file, because your Ubuntu side doesn't actually it keeps the file safe. So every time you can just replace that, so that's the way to do it. You can use you can create just your own scripts to do multiple commands one at a time, so to save you time. All right? So these are the commands that you need for this file system. Okay? This probably will also be in your recitation slides for your quick access. So Pintos make disk is a command that actually creates that virtual disk drive. You can give it the name and the size in megabytes, right? So this will create a new file in your Ubuntu, and then Pintos-F-Q asks the Pintos script to format its hard drive, right? So then it will be partitioned and then usable. -Q will ask Pintos to quit and don't actually boot up the kernel. Then you have the -P, which is the put. So you can ask the Pintos script that, hey, I have a file here. This address is in your Ubuntu. I have a file here. Put it in your file disk as you give it an alias like echo. You can change the name. I think even if you don't do that by default, it takes the same file name. And then -Q. Remember, these have the spaces, the number of dash, everything matters. So this will actually tell the Pintos that, hey, I want to put a file into the file list before booting, and then quit right after booting. The Q, this one actually will tell it to, okay, boot, run this user program, and then quit. And now this can all add up to each other. That's the way the testing scripts work. So because the testing script does not know if you have the file disk, is it ready or whatever, by itself it's just in one command, create a file disk and format it, and then put this file in it, and then run it, and then exit. Right? So it's not actually in order, but you get the idea. You can use such scripts from the test scripts, and then just use those as well. Or you can make your own scripts again to prepare and then copy, and then you can just modify your kernel and then start running. All right? So, however, we are assuming that there is a file here in the examples or tests that we want to copy, right? In your host file, there is no such file right now. There is echo.c, but there is no echo binary. And that does not get generated whenever you call make check, make rate, because whatever you're doing is going to be in your user prog, and your kernel will be generated. These examples or test files are different. So you actually have to go to this example folder and call a make. There are a bunch of example, C programs that you can basically run in your Ubuntu. They're just like C programs. But you're going to make them, and then so to generate the binaries, so then you can copy those binaries into your Pintos virtual disk drive, so your Pintos can also run. These are going to be compatible C programs, so their binary can be run in your Ubuntu, in your actual host Ubuntu, or in the Pintos. All of them are x86 compatible, right? So, user program directory is going to basically be most of your work. The file system directory, you might need to take a look at how the files sys.h and .c, how they access files within that disk drive. You don't actually have to understand all the disk block or devices or how inodes work. That's just up to you if you want to of course read up, but not necessarily for Project-2. The examples directory, there are a bunch of examples that you can basically use on your Pintos as user programs. You can also add your own user programs. hello world. You can like create a hello world program and then, add it to it. Or modify those, like, you can modify one of the programs to print out stuff that you want or do something. And obviously the test that actually will be in your grading, okay? Any question? Come on, ask questions if you have. Should I just move on? Okay. So you still have some work in thread.cnh because, again, remember, threads are part of the processes, and actually each process has one thread. And then you have to implement probably some, data structs, add something to be able to, allow a relationship between a parent process and a child process, or file descriptors. You might need to, not so much modification, but still. The process and H is a lot of the things that you want to handle between the processes, and also the setup stack for our argument passing. All of this will happen in this. The syscall.cnh has the most lines added because right now it's just 5 lines. It's just like an empty function, a syscall handler, and that does nothing, and it has to do everything. So I think it's I don't know. We're going to take a look. It's 600 lines of code or something. The exception.cnh is something, only one part of it, which is the page fault, is when, as I said, when a program tries to access invalid memory, then an exception happens, and that exception is the page fault, and then that's kind of like an interrupt, where the OS now should take a look at, okay, what's going on? Who tried access where? What was the problem? Right? So this will help you to modify, to ease up one part of your project. And these are just a page directory, so you don't actually need to modify any of this, but you can just read them and call some of those whenever you want to implement safe memory access. So again, the design doc, you have to obviously read a lot of the code and understand all of them, and then have an idea of, okay, what are we going to do? How are we going to implement this part? How are we going to implement this part? How are we going to satisfy this problem? How are we going to avoid this issue? And then again, just like your problem, project 1, make sure you put enough time in your design doc, because that's going to help you down the road with the implementation. And again, just the same thing. The template is there. You can leave the header as is. As you have realized, our course is not 140. Doesn't matter. Don't change anything. Don't change it to PDF doc, whatever. Just keep it simple. We love TXT files for submissions, right? So just modify your groups, members, and email addresses, and then start answering the questions, right? So, for example, argument passing. What are the data structs? The algorithms, rationale, everything. Okay? So, now we're going to go over to the implementation. You have to understand some of this for your design doc, obviously. So, whenever you want, for Project 2, there are different parts. One is argument passing, which is whenever you're calling a user programs, you want to pass the arguments, in the command line, so that the user program can actually use those. Safe memory access, when a user program wants to access memory, and how to ensure it will be safe. Whenever it's passing those memories to kernel, how to ensure there's no issue. System call infrastructure, and then the system calls. And then process termination messages, which is easy, relatively, and then denying rights to executable. So these are things that you have to implement. Starting with argument passing. So, as I said, you got the entry point to the user programs. The kernel boots up and then calls some of the functions, loads up a user program, and then starts running, right? Now, as a user program, I have no idea whatsoever about the OS, right? I only know my own stack pointer, and I don't know even where in memory it is, right? I have an idea of virtual memory, but I don't know physically. So here's my stack. And I have started. What I'm going to do again is just take a look at my own stack and then read arguments and then start using them, right? So right now there's nothing there. Before actually executing the binary or jumping to that function, The OS should now provide this, right? So read up the command lines and say, okay, how many arguments there are. I'm going to like put it like there, put it like there, and then, you know, it looks nice. Okay, now you can go ahead and run. Now it is set up, right? It is important to look exactly as expected by the user program, okay? It might look a little bit stupid. That's how it is. Like, you know, compatibility and convention, you have to know it. So, the kernel knows the whole command line. The kernel knows that I want to run bin ls with the, you know, the rest of the arguments. So the first thing for the kernel is to parse this itself, to first of all find, there's a slash here, to find the actual address of the executable itself, and then the rest of the arguments one by one. They are separated by one or more spaces. And then implement this string parsing by the strtok. It tokenizes. It's a little bit weird, but if you could just take a look at a couple of examples, it's actually pretty clear, right? So you can use this to do this. Again, this should happen in kernel before the call. So now it currently lacks the argument passing, and right now what is happening is that the stack pointer is pointing to the physical base. You remember, the physical base is the exact edge between the user memory and kernel memory. So right now what's happening is that the stack pointer is right below the kernel. So the user doesn't have any idea. It just like, you know, wakes up and it tries to read the first byte from its stack, right? And then it actually tries to access kernel memory. So right now the user program does not do nothing. Why? Because again, the first thing the user program does in its main function is that it tries to access its arguments in a stack. Right now the stack is right pointing to the kernel. So the first byte that it tries to access is kernel memory, and then there's a page vault, and then it crashes. Right? So first thing that you can do, at least to avoid this without any meaning, is to convert this line, stack pointer fizz base, to stack pointer fizz base minus 12. Now why is that? Because we're going to actually take a look at how the layout is, but because it's like physical base is here, so it's kernel above here. So right now, a stack pointer is right here. If you just move it at least 12 bytes here, just moving the pointer, not even putting anything here, just moving here. So now when the user program tries to access something, it's zero, it's junk, it doesn't have any meaning, but at least it's in the user address, virtual address, so it's not accessing a kernel, right? And at least it doesn't crash immediately. So this is the first thing that you can do, but then this 12 definitely going to be dynamic, and then it's not just going to be empty. You have to put stuff there later. And also, as we said, the kernel calls the load process and process execute, and then calls the process wait on it. So that the expected behavior is that the user program runs, it calls exit, and then the process wait unblocks the initial thread. That's how it should like wait. Whenever a process wants to wait for the other thread or process, they should just like block or sema down on something, and then whenever the process is done, then they signal so the parent process knows that the child is done, and then they can get the exit status. Okay, were you finished? Did you fail? Whatever. Right now, the process wait does nothing. It just immediately returns. So you have like two threads. The parent thread creates the child thread, and then calls the process wait on that, but it doesn't do anything. So basically, the child even doesn't get any time. The parent process, which is the initial kernel thread, finishes and then shuts down the whole system. That's it. So for now, again, without any meaning, instead of this, you change it to an infinite loop. So your kernel basically freezes there, but then the second thread at least gets to run. The user programs get to run. Your Pintos does not finish, so that's why you will actually still fail all of the tests, because all of the tests will time out. But at least you see the result of the user program. All right? Now, so when you have like bin ls-l foobar, this is like, let's say this is the command line, right? So what kernel needs to do is that it needs to set up the stack. So this is the stack, let's say, it grows down. the user, from the user perspective, when the stack pointer is here, the first immediate thing in the stack always is the return address. Because whenever you are in a function, even if you don't read anything, if you don't have any, local variable or anything, you have to be able to return to whoever called you, right? So return address is the address that when you call return from a function, you jump back to that address, right? That's the way how a function knows where to return. Now, in the main function, remember, main function is not supposed to return anywhere because main function is the entry point to the binary. A user program, when started, is not expected to return anywhere. It's expected to run and finish. Finish means calling exit system call. It tells the operating system that, hey, I'm done, kill me. It's not supposed to return. But still, it's a function, so it needs a return address. So that's why it's called a fake return address, and the address is 0. So in any case, if the user program had an instruction to return, it will try to access null pointer, and then the operating system crashes it. Right? Remember, this has been set up by the operating system, so the user cannot change this. So this is supposed to be 0. Now, the next immediate byte above this is the number of arguments. So again, the user program doesn't have any idea how many arguments it has. This is the way that it looks. Okay, I have 4 arguments. So I should look 4 more arguments above it. What are the arguments? Maybe they are 3 characters. Maybe they are more. I don't know. That's how the stack should be set up. So above the argc is a pointer argv, which is like a double pointer. Like the char star star. That it points just to the pointer above it. I don't know exactly why it basically does not. It allows this argv to be instead of like a stack in somewhere else, but don't worry about it. So then argv0 is again a pointer to the first argument. It's a pointer somewhere else, and then this is the rest of the stack. And then the next pointer points to the next argument. The next pointer points to the next argument. The next pointer points to the next argument. These are all the arguments in the command line. And then finally, there is another null pointer set for separating these. Okay? And whenever you're using and setting up a stack, if you want to take a look at how my stack looks before calling the user program, you're going to use the hex dump in your kernel. This actually is pretty useful. We're going to take a look at an example. All right? So you remember this, right? This is the layout. The fizz base is at 3 GB. This is the hex address of that. And then above it is kernel virtual memory. It's not accessible by user programs. And so this user stack, we have zoomed in, and we care only about this part. So right below the fizz base, which is this address, is this address. Instead of C000, it's BFFFFF. Well, there are 4 bytes, or like some bytes, like, BFFFFC, and D, and E, and F. Each of those bytes are these. Character B, character A, character R, and then a character 0 to indicate an end of a string. Right? Because it doesn't know that the argument is bar with 3 characters. It just starts at B and then goes on till a 0 null pointer. And then below that, at like this address, it's going to be foo with like a null pointer. Again, look at the length of this is like 4. So if this starts from here, it ends at here. Now this next argument will be -L null pointer. The length of it is 3. So if it should finish at this, it should start at this. And the next one is a little bit longer, 8 characters, moving, from here to here, all the way, starting from here, finishing before here. And then there is an alignment byte, and we're going to talk about it in the next slide. This can be 1, 2, or 3 bytes. And then, after putting the argument, now the length of these strings can vary, whatever, right? After these will be, this one is a null pointer, then a pointer to the 3rd argument, or the last argument. So this starts from here, so the value of this will be here. Then the next pointer, like this address should be here, at this address. So it's a little bit confusing, but you'll get an idea once you take a look at it. So sometimes you have to put a character, sometimes you have to put the address of that character somewhere else. You have to use pointers and %, star pointer, double pointers, star a star. You have to use all of these and have to know what are the differences between them. And if not, obviously, you got to take a look at least in the examples. Why it's like used star star here. So, and then the argv is like a pointer to this. It's a char star star. And then argc is an integer and the return address. Okay? So this has to be set up in your kernel before calling the function. Yes?
Does it go in that, if you go back, does it go in this order or should it be flipped upside down?
No. Well, this is okay. It's going to be a little bit confusing because when you call hex dump, it actually prints addresses from low to high because it's printing addresses and then the std out is just line by line. But usually it's just like this. The memory is lower is here. The way that it's like, in the diagrams, it's the memory lower, the lowest memory is here, highest memory is there. So that's and then the stack grows downwards. So whenever you push something to the stack pointer actually decrements.
Okay, so where is return address on the diagram to the left? Is it at the bottom of the
Yes, it's actually at it will be, the address is the smallest, it is the last item in the stack. So the stack actually on the computers actually work opposite than how you think of a stack putting on top.
Should it be right at the kernel memory user stack line? Is where return address is?
This one?
No, the other one.
This one?
Yeah.
Well, no, because the stack should grow, right? So you can't grow up because up is just like fixed, so you grow down.
Oh, so it grows below return address.
Yeah.
Okay.
Yeah. Whenever that you don't actually care. Whenever you push something with the instruction push, the CPU itself will decrement the stack pointer instead of incrementing it.
Okay. Yeah, I was just wondering if return address was on the other side, that you grew above.
No, it's all the way like this. So here is the same thing, but remember, instructions don't work on bytes on memory. Right? Whenever your CPU wants to load something, it doesn't actually load 1 byte. That's just like inefficient. Right? It loads in words, which are like 4 bytes at a time, 32 bits. Right? So it wants so that you can read an integer, which is like 4 bytes, 1 at a time. Right? We are talking about 32-bit architecture, by the way. So for that purpose, whenever CPU wants to load an integer, the memory should be aligned, in a multiple of 4 bytes. So that's why like the diagram is shown as here. So don't take a look at the above. So return address is a pointer. It's an integer. So it has to be aligned at an address which is a multiple of 4. Right? And then this like 4 bytes is like the return address. So the next integer above it, which is argc, again is an integer. So it's all aligned in 4. Right? You can see that. And but the arguments lengths are in characters and strings, so they can be arbitrary, right? That's why this padding is needed. So the kernel space that start at this address, the bytes right before this is FFFFF, this is FFFFD, this is, E, D, and C. So whenever you're putting these strings, you put them by character. They don't have to be aligned. This is just an example, and then it happened to be 4. But the last byte is always the null pointer, then, bar. And then the next argument is started here, like foo and then null. The next one is a shorter. So it's like -L and then null pointer. The next one starts from here because /bin/ls null pointer. Now, whenever the characters are done, because now you want to start pushing actual pointers and integers, you have to make sure that you put enough padding so that, this integer actually is here, not starting from here to here. So there might be some padding. See, you have to like make sure that, whenever you're pushing all this character here, you move back so that you are aligned with this, and then move down so that you now are aligned at this address, and you can start like putting integer. Also, take a look at how the little endianness of the Intel works. If you don't know, whenever you have like multiple bytes, for example, 4 bytes of integer, in your memory you have 2 ways to store it, either big endian or little endian. Big endian is actually how you actually think. I don't know for what reason Intel doesn't do it. Like, it's just like how it started. IBM did it. But whenever you have like 4 bytes, Intel actually stores it with the reverse byte order. So if my address that I want to store in this 4 bytes is BFFFFC, the instruction actually stores it like this. The first memory byte will be the FC, then the FF, then the FF, and then the BF. Just like, deal with it. So, but know it and don't get confused. That's the way the integers are stored. The characters are stored 1 byte at a time, so, they are different. Okay? So, now, this is the hex dump, which you're going to use in your kernel instead of like printf, because you can give it a memory address, and then it will print out the memory address aligned like that and beautifully. So you can tell it that, hey, show me, this, from this address, some number of bytes. Then it aligns itself with 16 bytes, always starting at, this one, and then prints out, so this will be the first byte, and then, going on and on and on. And so this will be the last byte in the user memory address. In your kernel, you can actually access below. You can look at it. It's fine. But this is where you care, because this is now has to be set up. So take a look at it, and then the printable stuff also will be here, the characters. So you can take a look. It's 0, and then the bar is set up there correctly, and then there's another 0, and then the foo is set up there, and then the 0 after dash L, and then the dash L itself, and then so all the way to bin. And then you can take a look here. Oh, this is my padding. If you've messed up, you can actually take a look at it here. And then this is like my null pointer. And then this will be my pointer to the last argument. Does it look right or not? BFFFFFFC. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C. So this pointer actually has a pointer to the bar. So that seems right. If it was like here, then okay, I messed up something when I was calculating this pointer. This actually gives you every information that you need for your setup stack. So, the memory access, whenever the user wants the kernel to do something, it will give a pointer to the kernel. Hey, I want to read a file, 100 bytes. Okay, where should I put that 100 bytes? The kernel asks, right? So the user program says, okay, kernel, I have a buffer here, and I want this file to read 100 bytes from, so please read 100 bytes and put it in my buffer. So it gives you, the kernel, a pointer. That is my buffer. Now, is this pointer safe? Is it pointing to somewhere that is not mapped? Now, the kernel doesn't know. If it just tries to access that pointer, then the kernel crashes. Right? Because that's the fault of a user program. But because it has been handed to the operating system, and now its operating system is running with, every access privilege, basically, then the operating system should not trust the user program. So if it's a null pointer, if it's a pointer to an onmapped, or other processes, or kernel virtual memory address, whatever, operating system should not treat those as, face value. So these are potential values with this. So there are two ways to approach it. First thing is whenever, you're given a pointer or a buffer from the user side, kernel basically checks it before accessing it. Okay, is this pointer accessing somewhere that is in the user memory first? Is the end of the buffer in the user virtual memory? Is all of the buffer, mapped page by page? Everything doesn't, seem fine. Okay, I'm going to now try to access this and, have no problem. So this is one way. It's safer, it's simpler, it's a little bit inefficient because most of the time user programs don't, pass on pointers. But if you do extra work, it's just like making it slow. The other way to do is basically directly access it and then see what happens. Most of the time, nothing happens. I mean, you still have to check that it's still in it's the user virtual memory. But if it's an invalid pointer, then the page fault happens, right? Normally, right now, when a page fault happens, it was because someone tried to access a wrong memory. And the assumption is that, kernel is safe. Kernel trusts itself. I don't usually access anywhere, that I'm not supposed to. So, if someone has, accessed somewhere wrong, it is probably a user program, right? So I'm just going to kill it. Right? Oops. So that's the way that kernel does now. Whenever a page fault handles, it just assumes that, okay, I trust myself. The problem is from a user program. I'm just going to kill it. Now it's different because now you might be the kernel side, but because of an error from a user program, the page fault is happening on the kernel side. So actually, if you kill it, you're killing the kernel. Right? So because of this problem, One way is to, instead of just assuming that the problem, was because of a user program and they're just killing, verifying that, okay, let me see. If it was a user program or it was a kernel that tried to access because of a user program. If this was the case, I should not kill the thread who would try to access that because that's a kernel. Instead, I got to do something smart so I can catch the user program instead and kill that. So that smart thing is like something that has been mentioned in this section, and it actually involves a bit of assembly work. You don't have to do it. You will probably be given enough information in the recitation, but we will provide you some help to, implement this piece of code here and then a piece of code here, and then do this, and then voila, it will work. You will be given enough information to understand why it's working, but it's easier to, implement. All right? You still can completely go ahead on this way and then implement it this way. That's up to you. Then we have to implement the system called infrastructure. Meaning, now the user program, argument passing, by the way, you have to be done with it like in 2 weeks. Because if you start struggling down the road, if you don't have argument passing, you don't pass anything. Now, if a user program tries to call the system call handler comes, it's a software interrupt. The operating system now has to take a look at the form. It has a very strict form of request. Now, operating system will take a look at it, and then based on this, will provide some service to that user program, right? So the first thing is to take a look at the stack pointer of the user, and then take a look at what is the system call that it wanted. Do you want to read a file? Do you want to write to a file? Do you want to exit? Do you want to wait? Whatever it is the system call number. So once I know what the service you need, then I will know what other information. So if you want to read a file, you will provide me with the name of a file. If you want to exit, then you don't provide me anything. So the first thing is that I understand what service it is, and then above that, the arguments for that service. Okay? And then basically you have to have a dummy skeleton for your interrupt handler, right? So if the request is wait, jump to this function. If the request is read, jump to this function. If the request is write, jump to this function. Just a dummy skeleton, right? Nothing in those functions. You can just printf, I'm here, and then, just return. So that you can at least make sure that, this is working. And then implement those functions one at a time so the, tests can start passing. And then if finally the operating system wants to do a service for the user, whatever, it will have to also pass a return value to the user so that when the user takes the CPU, then it knows was it successful, what was the result, whatever. And that will be put into FEAX. That will be in the CPU register, and the user program actually reads it. So then you start implementing the system calls. There are 13 system calls that you have to implement. And remember, there are a system calls that see in the lib user. Remember, whenever the user program has a printf and you compile it, that printf also ends up to a system call. So the binary side of the user should know what to do with that call, right? So this is this. Don't get confused. That system call has two sides. The user side, at the end of the printf, you actually see a snippet of assembly code, does something to the stack, push something values, those form that I said, and then finally calls a software interrupt. That's what it does. On the other side, this is right now is nothing, but your job is to take a look at the stack and understand what was the request, do it for the user, and then return the EAX value, and then return to the user. And so for the file system ones, you're going to use the file system, and because file system does not implement any synchronization, use just like a lock, global lock, whatever, so that only one thread at a time can access the file system, so there's no race condition. And then from the kernel, you have access to the file system, and I told you that you have functions such as open or read. Those all will work on a file struct. The user, however, they don't have the file structs, right? They have a file descriptor. So open a file for me, and then the operating system tells you that, okay, I opened this file, and now whenever you want this file, you can call it with 143. So next time, the user can tell the operating system, okay, you remember the 143 that you opened for me? write this to it, read it, whatever. So user programs use what is called as like file descriptors, which is that number which is assigned by the operating system itself. They don't have any idea about the internal working of the operating system. Now the operating system, however, has to know, okay, what was 143 that you are telling me? It was this file. So I have to basically have a mapping that whenever, like, I open this file, I assign you this number, and whenever you tell me this number, I should remember which file it is, right? Because there might be other user programs, multiple files, I have to keep all of this information. So this will be part of your kernel. So next is the cd out and the cd in. So when user programs actually want to access the console or to write something or print something, or when they want to actually read something from the keyboard, again, this is also I/O, and they have to request it through the system calls and ask the operating system to do this. So the way that they do is actually it's the same as reading a file or writing to a file or reading from a file. So when a user program wants to print out something on the screen, it's as if writing something to a file, but that file is very specific. The file descriptor is 1. And when a user wants to read from the keyboard, it's as if they want to read from a file. And again, that file is specific with the file descriptor number 0. So when they do this is like different. Operating system does not need to like access any file, but instead, like if the user program wants to print out something on the screen, they actually will tell the operating system that I want to write to file number 1 on this end. Operating system, when receives that system call, which is like, writing to file number 1, it does not check any mapping, because again, this is like a fixed number. So if you want to like write to file number 1, okay, gotcha, I know what you want to do. You want to like write something to the console. So on the kernel side, you can use put buff and put char functions. Use these to whatever that the user wants to print out, just like access them byte by byte or as a string, and then just like you print it on the console. Or if they want to again read from a file, and then they say like read from file number 0, then the operating system doesn't need to check any file or access to make sure that this file is known. They want to read from the console. So operating system instead can actually use input get C to get like characters from the keyboard, and then fill that buffer for the user program. And so just remember, because file descriptor numbers 0 and 1 are reserved for this purpose, then when a user program actually wants to open a file and access a file, they give the operating system the name. They say, okay, this is the system call for file open. So I'm going to write down. I'm going to like, I need a system call number or whatever, file open. This is the name of the file. I've put the name of the file in this buffer at this address. And then, then give me a file descriptor number. So, and then this will be there, and then the interrupt will be called, and then the operating system, comes alive and then checks and realizes that, okay, this is an interrupt. The system called interrupt handler will actually go and then look at the stack of the user program. So, first, again, at the top of the stack, what is it that you want? Okay, this is a request to read from a file, or first open a file. Okay, what file? Look at this pointer. You are pointing to that buffer in your program. Again, remember, safe memory access. Considering this buffer is inside the user space memory and mapped, so then the kernel can actually take a look at this buffer to read the file name. The file name itself won't be in the stack. It will be only a pointer to a buffer string of the file name. So then the operating system can say, okay, you want to open this file. All right, I'm going to go use the file system that I have and open this file, and then I'm going to associate a file descriptor to this file struct. And remember, operating system works with the struct file. And then I do this mapping, and then I'm going to give you a file descriptor for this file. So whenever you want to like call this file open, close, read, write, whatever, this is the file descriptor that you're going to use. And that's going to go with the EAX, right? So that will be the file descriptor. However, you have to remember that this file descriptor that the kernel is associating cannot be 0 or 1, so that, there is no conflict. So you just like basically have to start from number 2, and then you can just like start incrementing. So next file will be 3, next file will be 4, whatever, right? So this is something that the kernel should do. Then some of the system calls are related to processes. So, for example, exit. When a user program calls exit with a status, that means that, okay, I'm done. I want to like exit. I want kernel to free my resources. And, the result of my, execution is, this is status, right? So if my parent is waiting on me, for example, let them know, right? I'm just going to say bye, and that's just like what I'm leaving behind. So this is an exit system call, and upon this system call, operating system should free the resources of a process, the allocated memory, which are specific to that process, and also save this status somewhere, because this is important. If you save the status in the process, if the process is exiting, then either you're not freeing resources, or if you free the resources of this process, and then that status also gets freed, then the parent does not have access. Maybe the parent has not wait on it yet. Maybe the parent wants to like see the status of the child later on. But if you now free this, everything here, then there's nothing to access. So there should be a difference, destruct somewhere, so that, both child and parent probably can access, and then you can save this as a kernel, save the status there, so when the child gets wiped out, then that status is still there later on if the parent wants to access. A child can exit before the parent performs the wait. This is also important. So when a parent process creates a child, in the kernel you get to actually duplicate some of the information or allocate new memory for this process, whatever, and then also obviously also a thread will be eventually created for that process. Now, remember, a parent may or may not wait on a child, and even immediately, if they wait for that child, there is a race condition. So the moment that I create the child, if then the parent gets preempted, now the child gets to run, and then maybe it's like a very short process, gets created, loads, and then, starts running, and then finishes, and then call the stack, call the exit system call. Before the parents get the CPU again, and then call the wait. So the order of the execution can actually happen, and so there should be a kind of a synchronization between these. And then you gotta remember that a process can perform wait only for its children. So if a process just wants to wait for a random process, no, the kernel should not allow that. A process only can call wait on the processes that this process has made, right? So you have to again keep these information somewhere in your kernel so that you can check and see if a process is trying to wait on a process that is not its child. You have to fail that. And then a wait can be called twice. So if a process calls a wait on its child, and then some lines down the road again call the same wait on the same process, then you have to understand the first time that the process is waiting on that process, the parent process should be blocked. So the parent process is not running anymore. So the child process finishes, saves its status, and now, through the synchronization methods, the parent process will wake up and then get the information of this child. Now, what happens? Like if they wait for the same child again, the child is already gone, so they cannot like block for that process. Also, you may say, okay, we can just give them the same status, number, but that brings this process to confusion, like because they don't know if it was like the same or is it like new information. So the way to do it is basically only on the first call of wait you should do this. If the process calls wait on a child process that this process has waited it before, you have to basically fail this call. All right. Also, wait is it can be nested. So this process waits for its child while it's blocking. The child process, executes and then creates a grandchild and then waits for them. Now that process is waiting for this, and then this process is waiting for this, and then again, each should basically have separate information saved in the kernel. So you have to also, as I said, the process wait, you can turn it into an infinite loop, but eventually that's not the wait. So once the initial process exits, then the pintos should basically terminate and shut down, right? Otherwise, it will never, it will always just time out. So the wait itself, as I said, the parent process should block until the child process finishes, and then you have to use synchronization because the order can now change. So if the wait has already been successfully called on a child, successfully means that there is, the child actually exits, and then there's a status, and then you return it. So the next time it should be -1, the result of the wait. And if again the PID does not reference a child of the process, so if again the parent's just waiting on a random process, the result should be -1. And then again, you have to remember, the process can call wait on different ones or nested ones. And once you implement the process wait, then you can actually start the system call wait on top of process wait, because the process wait is the way, for example, that is already there, and operating system, the kernel, is waiting on the initial process. So you can basically implement it using that. So once you actually can implement in kernel waiting on a process and blocking this thread, then this can be also used in your syscall. So if this parent process calls the wait, you can use the process wait and its synchronization that you have implemented to basically satisfy that. And the wait itself involves the most of the work, again, because of all this parent and child, all the ordering. What if that exits before this? What if it's called wait before that? What if what happens if that exits and the parent doesn't wait at all? Are you gonna still leave some data here when nobody cares about it? What happens if the parent gets to exit without waiting on the child, and now when the child exits, again, are you gonna leave some information here without no one actually caring about it? So that's kind of memory leak. So you have to think about okay, this information should be there as long as it might be needed, as long as either the child or parent may access it. So this is again a hint and important for the avoiding memory leak there. All right. So the next one is exit. So this is relatively easy, and you can start with this system call, and it will basically just terminate the user program and return the status to the kernel. Again, we just said how it's supposed to do work, but again, the data structs are still shared. So probably you're going to share the same data struct for exit and wait, because the status is just it should be saved somewhere. And also on the exit system call, a termination message should be printed out. Tests basically look for that. So one of the things that they look for is that upon a termination of a process, they print out a specific type of message, the name of the user program, and their exit status. Again, this communication between the child and parents should happen in exit and wait both. You have to share this information. All right. So exec in CentOS acts as both fork and exec-v. Right. So when a process calls exec, they want to create a separate process, and they already will give you what file name that process should load, right? So they will give the command line, and so this system call, when it's initiated, the operating system should create a child process, and then that child process should start running this program, right? And now this is also important. This exec might fail, right? For example, if a parent process wants to create a child process and then ask to, okay, I want the program CP, as our example, to, for this child process, I want it to run CP program. Okay, what if CP is not there? If CP is not there in the virtual hard disk, then exec should be able to fail. But at some point, you are creating the second thread. So when you create the second thread, this thread will start the loading of the process, right? Loading the process, the new from the file, and then setting up its stack, and so on and so on. Within all this time, the initial thread can get scheduled and then just continue. But it won't know if this thread will successfully load the file and start the execution of the process or not. So it's important for you to understand that you should use synchronization to ensure this, that the parent process, that the execution thread in the parent process should block until the new thread starts, loads the program, either finishes successfully or fails, and then be able to communicate this to that thread. So then this thread can return from exec system call with a pass or fail result. Again, that's the short story. We'll probably get into the details in recitations, but this is important for the exec. This synchronization, again, is needed. So, other system calls that are related to files. These are relatively easier both to understand and implement because they are somewhat like wrappers around existing system APIs. So, not like API, but basically the functions or libraries that you have in file systems. So system calls related to files are either create, so the user program wants to create a file with the name and the initial size, and then it's either successful, or failed. Removing a file, again, Boolean, open a file, and then giving, returning a file descriptor. And then using that file descriptor to retrieve the file size as an integer, reading from that file with the file descriptor so many bytes into this buffer, and then this will be the actual number of bytes read. So I think you've already you might have also used read in just higher level programming. So when you want to read 1,000 bytes from this file and the file is only 500 bytes total, then the function will return 500 to you, so you know that the file was, for whatever reason, it could only read 500 bytes from it. If it could read the whole 1,000 bytes, then this will be 1,000. The same goes with the write. So I want to write to a file given the file descriptor. And then what I want to write to that file, I have saved in this buffer, and the length is in size, right? So you're telling the kernel that, okay, I have a buffer here, I have a file in mind, and I have a number of bytes. So please take a look at this buffer, take so many bytes, and then write into that file. It will return the actual number of bytes written. And I can ask the operating system to seek inside a file, to a different, to a specific position. That actually is just void because there's this is just like this position is only saved inside the kernel itself. It's nothing actually doing to the file itself. And then it will return where the position is in that file, and then also closing a file eventually. So the create, remove, and open, they work on the file name. So the user program will have a buffer somewhere in its memory, and then have a file name there, and then gives the pointer to that buffer to the kernel. And then otherwise it uses the file descriptor. So you can also already see that on the system call side now, when the operating system, receives a system call, it first checks the system call number. Okay, what do you want to do? If you want to open, then what you should probably provide right above this system call number is a pointer to a buffer, because you have to pass me a file name. So then in your system call handler, based on the type of the system call, what you should expect. If the system call is read, then you gotta tell, okay, the user program wants the operating system to read from a file. So I need a file descriptor, and I need a buffer, and I need the number of bytes. So you can take a look at 3 integers above in the stack pointer. So the first one would be, for example, the order is actually defined there. I think the first one is the file descriptor, then a pointer to the buffer, then an integer which indicates the size. Okay? And so this is again a hint. So as you can already see, some of the system calls, they only have 1 argument. Some of the system calls have 3 arguments. So you should not just start to read a bunch of you can read as a kernel, but you have to at least be able to differentiate. If this is this system call, the only thing that the user actually put there for me is just file descriptor. If it's this system call, okay, now I need 3 arguments in this stack. All right. So again, you don't need to change the system call. The file system directory. You can just read if you want to take a look at it. And again, most of them are wrappers. So when you implement the mapping between the file descriptor and the file struct, then so if the user wants to read this file, you can check the mapping. Okay, what is this file descriptor? This is this file. I have already opened it, so I will just call read, and then whatever I get, I will pass on to the user. And again, for the robustness, it's different, but for functionality, you can just directly access the memory and then read the file and then copy it there. Or a safer or a better way is to actually allocate memory inside kernel space, read the buffer into the kernel space, and then be done with the file, and then try to copy the buffer to the user. This is also a safer way to do. Again, if the user program wants to write something to the file, instead of actually accessing the buffer and then writing it to a file, one way the kernel can do is allocate memory inside the kernel, allocate the same size of buffer, and then copy the buffer from the user program virtual memory to the kernel side, and then write this information to the file. This also prevents any race condition, for example, if this buffer is being modified. So basically, again, most of them will be then wrappers around the functions implemented in the kernel. So the main thing is that you maintain the mapping between the struct file and the file descriptors. And you also have to remember that the file descriptors are unique to the user program. So if this user program opens 3 files, file number 1 and 2 and 3, and then it gets some file descriptors, then another program, they cannot immediately ask for this file descriptor, because they have not opened a file. So they cannot access any file descriptor. They can only and then if they open the same file, the kernel, again, should not give them the same file descriptor, because that file descriptor is part of the other process. If they exit, and then, the kernel should free up their memory. So what should happen then? So the file descriptors are independent. That doesn't necessarily mean that the value of the file descriptors are different. So if process number 1 opens this file, and then the kernel assigns, file descriptor number 3, it's still fine. If now another process wants the same file, if the kernel gives them again 3, it's fine, as long as it can maintain and differentiate between this 3 and this 3. It's up to you. You can implement just a unique number and just remember, I'm just going to give the 3 to this process. The same file I'm also mapping to 4, and then I'm going to give 4 to that process. So this process only can call 3, that process only can call 4. This is one way to do it, and it's easier. You can just go on with it. It's fine, right? But as long as a process has not opened the file, they should not be able to access it. And then also you have to implement denying rights to the running process executable file. Remember, this process is running from an executable file on the virtual disk here, right? So as long as this process is running, no other process should be able to open and modify write basically to that file. Okay? So you have to be able to tell if a process starts off a file here. At that point, the kernel should basically remember that, that file now is being executed. So no process should be able to later on open that file and write to it. Once the process exits, they may do it again, but not before this is executing, right? And also, again, use just coarse synchronization just to simply, implement this, because if there's any race condition, if the two processes wants to run the file system, just, have a lock or something. All right. Now, the process termination message is something that we already mentioned. So whenever you use a process terminate, because it's called exit, or for any other reason, if they crash, for example, and then you want to free up the process resources, this message has to be printed for the name of the process, and then exit, and then the status, right? So the name is the same, the same name that is passed to the process execute, CP, args none, whatever, right? And then not the rest of the arguments, only the process, the file name itself. And you don't have to print this if the kernel thread that is not a user process terminates. So if a kernel thread creates a kernel thread, that's not a user process, right? Then if that thread is just exiting, you don't have to. I think it says it's optional. Or when the halt system call is invoked, you don't have to, because that process is not technically exiting, but they are asking the operating system to halt the system. So in that case, you don't have to. Actually, I think you should not do it. If a process fails to load, it's optional. Yeah, I think in these cases, actually, you should not print those messages, because again, the testing systems look for these outputs, and they mess with those if there's an extra print. The other thing is actually the the debugging messages that you print. Eventually, when you actually want to test, you have to disable them. You can have a way of having defining a variable, and whenever you want to print out debugging messages, you can just change the flag in the end, or just commenting it out whenever you want to add debugging messages, so that whenever you're testing, those are not there to mess with the result. Okay, so this part again is the denying rights to the executables. You have already some tools to do this. So, file deny writes function is already there. You can take a look at how it is being used, how to use it, but in your kernel, you still need some information. You have to keep some information for this purpose. Okay, what file is being, associated with what process whenever they were done. Okay, now I have to be able to, change it back. So, executable must be kept open as long as the process is running. Once they're finished, that you can re-enable it and close it. So this now we will move on to the suggested order of implementation. This is important. So because the argument passing, I think, is the first thing that you want to approach is so that the user program doesn't fail right at the moment. So again, change the ESP pointer to fizzbase -12 in the setup stack, and again, this way you are not setting up a stack, you're just giving exactly 3 integers. One is the fake address, one is argc, and one is argv. These are the minimum things that will be there, and that the user program may just access them. If there are no arguments, then argv is also not pointing to anywhere because argc is 0, right? But at least these 3 integers should be there. Once you do this, at least the user program gets to run. But immediately the whole system terminates because the process wait does not do anything. So also you have to turn it into an infinite loop. By doing only this and this, you at least allow the user program to run. The system will time out, but the user program will run, and whatever the program here is at this point, they cannot have any arguments, they cannot print f, they cannot, they are kind of useless, but at least they run. So now, but this gives you at least, let you start implementing for example, the write system call so that they can actually print, right? So then you have to actually implement the system called infrastructure, and just read the system call number from the user stack, and then dispatch to a dummy function. Just have in a skeleton. Then start implementing you can also implement the exit system call, but the important thing is the write system call to stdout. Even if you don't implement the write to the different file, a specific case of stdout, which is the console, you implement it in the kernel, because that way the user programs can actually print even without any argument. At least they can print hello. And that's important because no test will pass until you have any output. And also again, from your user programs, you can modify them. You can actually change the examples and or create a different example file, compile it, put it into the user the virtual disk, and then run it in your Pintos. And then this program now you can every time modify, right? Print out hello. And then you can at least make sure that, okay, my program is loading and it's printing out. Okay, so that's good news. Now, in the user program, you can modify. Okay, try to access your stack pointer and read a couple of bytes and see, right? Or take a look at your arguments that have been passed to you. Do they look okay, right? So these are the things that, again, the program only needs the printf to do so. So this will be the starting point, I would say. And so once you start that, there are definitely, debugging needed. So as I said, make sure for argument passing, you use Hex Dump. It's useful. Without it, it will be difficult a lot because you have no idea what you're doing to the memory. You might have a pointer pointing somewhere else, or having alignment issues, whatever. So Hex Dump is really helpful. Printf from the kernel can help you, but a lot of the times in this project you realize actually printf is not allowed, and for that you have to just start using others. So for example, backtraces or GDB. GDB is pretty useful. It is a little bit annoying at the start when you start using it. You might not feel comfortable and a little bit lost, but once you actually get to know a couple of steps, and it's very easy, it's gonna reveal a whole, a bunch of information to you that is otherwise difficult to guess, or use printf or whatever. So you can just like, breakpoint and then step by step run through the code and then look at the, what is this variable, what is this list, and then, eventually expect, okay, now I'm running this line, I expect this to happen, but then you realize, oh, okay, now I realize what's going on. This line is, whatever, accessing something. So GDB is pretty useful. I'm just like, take that from me. This is also an example for PrinToast running PrinToast with GDB. Remember that there are some places here a space, here a space. There is no space here. The same thing you actually do with Project-2, that you have to like format or use -q and all these. So just like pay attention to the dash. So some of these examples will be in your recitation slide. So just take a look at these dashes and spaces, and I think this hopefully you can also, you can use this in Project-1. Hopefully you're already using them. So this is how much, almost like an estimation of how much code and what files you need to modify. There is a bit of in thread that you need to modify, exception.c, not much as I said, but just a tiny bit. And most of the work will be in your system called C and H as well. Yeah. Again, this also depends. Like this is one reference solution, so you can have different ways of obviously, but this just gives you an idea. Most of the work is in system call at C and process at C. All right. So now the testing is similar to the project one. So it's just like that. You have to run it inside the user prog folder. So you can go inside the user prog folder. And then, run the make check and make grade work exactly the same. However, there are different tests. So instead of like just 27 tests, there are actually more tests, even more tests, and there are basically 80 tests. But however, the tests are different. So in project number 1, tests are separate for alarm clock, priority, and LFQS, right? So in the project number 2, the tests are different. The tests are functionality tests and robustness tests, right? So the functionality tests actually are user programs that are behaving normally, and then they expect some functionality from the kernel, right? So I want to read a file. Can I read it or not? That's it, right? So this is an example. So this is for argument passing, right? So this user program starts, take a look at its arguments, and then just like prints them out. That's it. Now, the tester script will check the user program for this args 1, 2. I'm calling the args program with arguments like 1 and 2. Did it like print out all the expected print messages? So begin. argc is 3 because it's supposed to have like 3, 1, 2, 3, and then argv0 is args, argv1 is 1, argv2 is 2, and argv3 is supposed to be null, and then end. If these are all printed, then the functionality the expected from this user program is satisfied, right? So then this test passed. So once you start like implementing pieces of code, then you're basically providing functionality, and then tests start like passing. Now you can obviously take a look at what the tests are doing and what is expected of them, and that will give you an idea where you're like missing, or where you should like start modifying or fixing. So the other tests are robustness. Robustness tests are basically programs who try to mess with your kernel, try to access somewhere that they're not supposed to, or try to do something stupid. And then, so the expected behavior, for example, is that, okay, if you are trying to access, dereference the null pointer, so if this message gets printed, congratulations, you have successfully dereferenced null, right? So the expected behavior is that the kernel actually does not do this, and then upon this, a page fault happens, and before continuing the rest of this program, which is like printing this, the kernel actually stops that program, right? And then otherwise, if this does not happen and we reach here, like, you should have exited with -1. So the expected behavior is that the kernel prints the termination message here. The bad read is the name of the test, executable, and then the exit status should be -1 because kernel is stopping the user program because of this reason, right? So some of the robustness are this. So if you implement a functionality, but the robustness tests are not like passing, that means that, you're not checking enough, you're not checking for null pointers or, bad behavior of a user program. On a normal behavior, you're treating them, okay, you have provided the functionality, but there's checks that you have to do and then you have missed, right? So the grading is again like make grade, and so the same thing, but there are different again points and different weights. If you want to basically calculate and then see, okay, what test has more weight and it's worth to invest my time, you can take a look at them. You will actually have all the information. I don't have them on this slide, but you have all the tests. And then all their points. Okay, this test is this many points, these tests is these many points. You have to take a look at, okay, what is the category of that test? Is it a functionality test, robustness test, or, this one or this one? Take a look at the, how much of the point is to the score, so that gives you an idea of the weight, and then say, okay, this test is more important than this test, so I'm going to go for it. But, however, I think, all right, sorry for the interruption. I think at 11 p.m. the system just shuts down itself without any warning or anything. So continuing, so you can take a look at, whatever you test, but I would actually suggest that you just follow the suggested order and start from, the pieces of code and, system calls one by one. You can divide and conquer, meaning, now you have more independent pieces of code that you can divide between your group mates. So, system calls are relatively independent enough that you can basically start, dividing them among yourself. So, okay, now your design document again is 10% of your Project-2 grade. 90% of the grade is the source code. The due dates are April 5th and April 19th, again 2 weeks apart. This will be a week, almost 10 days or almost 2 weeks after the spring break. So, you have enough time. But you can also start in the spring break thinking about, or at least reading the code and then understand how the, all the things that we have discussed, work in the Pintos. So, again, the make grade, whatever that it will give you out of 100, will just scale it down to 90%. So you can just make sure, whatever you get on the autograder, that's the same score that you get on your own machines. That should also happen in your project number 1. I think you're submitting, some of the groups have not submitted their source code yet on the autograder, so please do so. But I think by the time that you watch this lecture, it's already past the due date, so hopefully you don't miss any point. Alright, so the submission again is going to be through the autograder, both for design doc and for source code. I just want to note here that some of the files that you submitted on the autograder for design doc were corrupted. Please, again, this was something that we emphasize, that whenever you submit something autograder, it will print out. So if it doesn't print anything, that means your file was was not correct, or it was wrong, whatever. So there was something wrong going on. So please watch for when you submit on the autograder. Check for the results. All right. Again, you will have unlimited submissions, so submit. So we will have something to grade you, even if the last submission is wrong or there's some issue. Again, remember the due dates are all on Friday nights. So 5th of April is the design doc. 19th will be the source code. All right. And again, as we have like discussed this before, there will be no late submissions. You can start like implementing softer deadlines for yourself. And again, I hope really that you have learned your one lesson from the project one, and that is actually we mean it when we say, okay, projects in the operating system is huge and they take a lot of time. So please start early. Don't leave it for the last week. It is just not enough time to do so. All right. So hopefully we won't have like a hectic week around mid-April. All right. So finalize your groups on AutoGrader just to check. For source codes, again, I just transferred the groups from the design doc. If you want to like make sure, check them. Finish and submit by the end of this week. If you are considering changing your groups, send an email before starting PA2. Don't wait for too long, because again, groups might start like thinking about designs and whatever. So we don't want to actually wait for that long. So if you're considering, email as soon as possible so we can think of whatever number of like groups. If they want to merge, we regroup them or something. And I hope you enjoy your break. And I'm going to see you on 26th of March, hopefully. All right? And if there's any question, you can post it on Piazza. You can email me. And see you on March 26th.